we are Spacecraft Thermal Management Systems. My name is Carlos Macias, and I'm the project manager.
My name is Fadi Simon. I'm the E team lead.
My name is Brandon Garajeda, and I'm the team lead for the vacuum chamber design team.
My name is Amber Charlie, and I'm the team lead for tungsten.
This is the agenda for our presentation, and it goes as follows. The top picture is a schematic for our variable electrochromic device. The bottom pictures are physical representations of that schematic. The bottom left is our nickel slide, the middle is our gel electrolyte, and the rightmost picture is our tungsten slide.
Some background for our project. CubeSats in low Earth orbit often experience variable heat fluxes coming from the sun. This causes temperature variations that are pretty severe for a small CubeSat. A good solution to this would be a variable emissivity device. The way these work is they change the emissivity of their surfaces, regulating how much heat is absorbed or emitted in space. Our project is interested in the performance and the manufacturing process of these variable emissivity devices. Our main objective is to investigate these VEDs in the hopes of achieving an improvement in manufacturing costs and the performance of these VEDs. Some goals are to develop a manufacturing process that yields in a consistent deposition of the transition metal oxides, as well as to create a transparent electrolytic medium for electrochromic function. We also want to implement a vacuum chamber to simulate the conditions found in low Earth orbit by these CubeSats for testing. And then we also want to determine whether EE technology can be used in space application.
Our requirements are, we want the vacuum team to build a chamber that can withstand pressures in the high vacuum regime. The gel electrolyte team wants to produce a gel with a conductivity that is greater than 2 × 10⁻⁴ Siemens per centimeter and a transmittance that is greater than 70%. SCMS wants our VED to have an emissivity range of 0.2 to 0.8. As for the chemical teams, they want a consistent slide deposition that only gives a plus or minus 5% difference in transmission and an opacity with 20% transmission for the nickel slides.
The timeline displayed shows the milestones completed by the design-based teams. This quarter, a preliminary vacuum chamber design system was achieved. Unfortunately, there were some errors in obtaining the license for the simulation meant to simulate the satellite orbit. The remaining work you see here will be undertaken next quarter. Next is for the milestone for the chemical-based teams. This quarter, they were able to synthesize a preliminary electrochromic gel, as well as produce a nickel-based sample with high opacity. Again, the remaining work will be undertaken next quarter. Lastly would be the milestones of the database teams. They made a substantial amount of progress in constructing a test setup for emissivity measurements, as well as designing and manufacturing an electrode holder. The remaining work, again, will be undertaken next quarter.
The subsystem breakdown is as follows. The rightmost picture displays the physical representation of that breakdown. The project manager and the advisors coordinate the direction of the team. They also deal with specific aspects of the team that do not intersect with each other. The team direction is proposed to the team leads and an approach decided upon in order to move forward. Team leads break down their goals and distribute them to their sub-team members.
Now moving forward with the progress of each sub-team. For the nickel team, their goal is to produce nickel oxide films that have 4 main properties, and that is opacity, electrochromism, uniformity, and life cycle. And their progress for this quarter is that they've tested different variables that affect the opacity of the nickel films, and they've tested different variables such as ammonium hydroxide concentration and deposition time. And for next quarter, they want to continue improving the design procedures and also test the life cycle of the films. And as you can see in figure 4, these are the nickel slides that were produced with 20 milliliters of 30% ammonium hydroxide concentration.
The gel electrolyte team is looking to develop a synthesis procedure for an electrolyte gel that is both viscous and transparent, as well as having a minimum ionic conductivity of 2 × 10⁻⁴ Siemens per centimeter. The progress this quarter has been electing 2 cellulose-derived gel formers, one for PMMA and one for CMC. The gel containing different percentages of PMMA were synthesized, but only the 30 weight percent PMMA gel had a transparency and a viscosity within the criteria. This gel can be seen in figure 5. This picture was taken after the cell was dried. Control methods for PMMA gel ionic conductivity is currently being developed with the Spacecraft team.
As for the tungsten team, we want to synthesize tungsten oxide films and we want to be able to control its characteristics based off of our chemical procedures. And for the progress this quarter, this is our first time running the experiment with the closed system and also constant temperature regulation. And so far, we've been able to narrow down which concentrations of hydrochloric acid is best for the deposition. And as you can see in figure 6, these are 3 different films that vary in thickness and particle size. And for next quarter, we want to be able to test and confirm our results. And we would also like to image and characterize with SEM and X-ray. As for the spectral team, their goal is to investigate the optical properties of the different slides and to develop an experiment for testing electrochemical properties. And for this quarter, they have evaluated chemical slides for transmission, emissivity, and uniformity. And they've begun investigating the electrical properties for the electrolyte gel. And they've also started designing a testing setup for the potential stack. And as you can see in figure 7, these are different tests of different nickel oxide slides. You can see they're pretty uniform as they overlap each other. And for figure 8, this is a graph of the cumulative charge of both the dry and baked electrolyte gel.
The goal of the space team is to use advanced software to simulate the orbital mechanics of the UCI CubeSat. This is to simulate the environmental factors it may experience while in orbit. These simulations will also be run on multiple platforms in order to further refine the simulations. The progress made so far is that the space team has created several simulations of orbital telemetry. As far as future work is concerned, they will continue to refine the simulation properties, experiment with orbital parameters, and generate reports of radiation levels, as well as examine the magnetic flux and other environmental factors experienced by the satellite. For the vacuum team, the primary objective is to design, manufacture, and test a vacuum chamber capable of simulating conditions found in low Earth orbit. This is to ensure the quality, effectiveness, and behavior of the electrochromic thin film sample. The progress this quarter was that the vacuum team was able to successfully produce a preliminary design of the vacuum chamber and the system that connects to it. Next quarter, they will undertake initiate the manufacturing process of the vacuum chamber, therefore building, assembling, and testing the vacuum chamber design.
For the E team, our goal is to test the thermal properties of the e-paper displays to assess whether they are a good alternative to conventional PEDs. So far, we have tested the e-paper using a proof of concept test where we found a 5-degree Fahrenheit difference in temperature based off different display settings. This suggests that there is an emissivity change when changing the display setting. Currently, we are working on constructing a test setup for the thermal conductivity of the e-paper. This is necessary for a future test we would like to do to measure the actual emissivity of the e-paper itself. We would also like to measure the reflectance of the e-paper using a spectrometer in the future.
To summarize it all, teams have used this initial quarter to establish themselves because more than 90% of the team members were new. Much of STMS's resources were focused on assimilating all new members and making sure each team knew what they were doing before they started their work. Most teams have done preliminary work so far that has helped lay down the foundation for more detailed research with the quarter to come. The work that will be produced next quarter will be used to make final decisions on the official procedures that will be followed to produce our slides, the material selection of our gel, and it will help verify whether or not the ink is a formidable solution for our problem. Thank you.